already well equipped with his mic, who will speak on theory and practice. Paul Madden, who is, I think, Professor of Physical Chemistry, something like this you are. So you are well suited for telling us a little bit about the physical chemistry of thorium molten salts.
Well, thank you very much to the organizers for the invitation. I'm delighted to be here in this environment, in this company. I've been working on developing methods to predict the properties of molten salts, essentially from first principles, for about 25 years now. But in the last 3 or 4 years, I've been involved with my co-workers here in Paris in this AVOL project, which has been mentioned several times today. The AVOL project is a Euratom-sponsored project. It involves about 13 groups across Europe and collaboration with a Russian group also working in this sort of area. And it's to scope out, technically, what's required to build a molten salt fast reactor. So the strength of this program is that it will look at all aspects of a whole system. So it will look at, I shall obviously be interested in the reactor and the molten salt that's there, but people are working on the heat exchangers, the cooling system, the generators, the safety features, the transient analysis, the evolution of the inventory in the system as it runs forward. So all aspects of this system are being considered within the scope of the project. The idea being that if any of these links starts to fail, in other words, if one can't find a technology which will work in conjunction with the other working technologies, then one has to start thinking again about the fundamental design elements. So, as I said, I'd like to speak about this because it sets a context for what I want to say about modeling molten salts. So here's the core of the reactor. It's aiming at generating 1.5 gigawatts. It will run with a solvent system, which is a lithium fluoride, thorium fluoride eutectic, and it will run either with uranium-233. The design has been done with uranium-233 at about a 3 or 4% level in the salt, or alternatively a startup composition made of plutonium and minor actinides. There'll be a fertile blanket which surrounds the reactor vessel, and the kind of physical properties that we'll be dealing with here in this system is its operating temperature should be in this regime. As we'll see, the lower bound here is really set by the freezing point of this mixture, albeit a eutectic, and the upper limit is really to control the corrosion in the solid elements. And I should have said that one of the other parts of the study is alloy work to look at the corrosion resistance of the containment materials and also the alloys used in making mechanical elements like the pumps. Now, the interesting feature here is the volume and also the cycle time. So it's perhaps not generally appreciated, but the contents of this vessel will be blown through here in about 4 seconds. It will be renewed about every 4 seconds. So clearly these pumps, at least in this design, are playing a fairly fundamental role. As well as the neutronics aspects, there will also be the chemistry of controlling the salt composition to control the amount of fissile material that's present, to control the redox potential of the salt in order to avoid corrosion, and also to extract uranium-233 here. So the physical separation, there'll be at least 2 processes there. There'll be a bubbling system to extract gaseous products and also particles in suspension, and then a pyrochemical reprocessing unit here. And the modeling of this whole concept builds in certain assumptions about the rate at which reprocessing could be carried out, and the technologies are being developed to present a practical scheme for reprocessing on the timescales which are demanded by the evolution of this system towards a stable inventory. So, for example, here's some modeling which Elsamel Lucot, who will be speaking on Wednesday, has been involved in, which involves coupled thermal hydraulic and also neutronics. So these these velocity and temperature fields here have worked through all of the neutronic reactions, the way that heat gets generated within the system, and also the way the hydrodynamics of this particular design. And clearly, this is design work to try to optimize the shape of the reactor vessel, perhaps to maximize the amount of convective flow through the system. So to do this kind of thing, you need lots of properties of molten salts. You need various thermodynamic properties. I've already mentioned melting points. You need transport properties like viscosities, thermal conductivities, and so on. And you also need chemical properties, because you need to know about these reprocessing elements, what will work, what won't work, and how maybe you can control the chemical properties. And the salts, as I'll stress in a moment, are multi-component molten salts, and you need these over a wide range of temperatures. So these are the types of properties that you're interested in. So we know, for example, for this lithium fluoride, thorium fluoride, that the phase diagram looks like this. So this is the liquid region up here. This is this eutectic composition. And you remember that I was talking about operating this reactor in this sort of temperature range between about 650 and 750 degrees Celsius. But you can see the sorts of issues which might well arise, because if the composition of the melt was to change by not too much, you start to run into freezing. And clearly that would be very undesirable if something like that started to happen, in particular in your heat exchangers. You also need transport properties. Now, some properties of the basic eutectic mixture have been measured, in fact, in Russia. So these were the kind of formulae which went into the hydraulic modeling that I just showed you. So the point I would like to stress is that the properties of these melts are actually, what you need is the properties of multi-component melts. Lithium fluoride, thorium fluoride is all very well as a solvent system, but as we've been hearing, you'd need a fissile component of about 3 or 4% in there. So it's actually a ternary mixture. So it's a quaternary mixture. And to get properties of those multi-component melts, whether that, for example, that plutonium would start to plate itself out in the heat exchanger. You need to know about such things for all aspects of the design of the reactor of that level of complexity. So you need to know about multi-component molten salts over a wide range of temperatures, and also for the different compositions, because you're chemically reprocessing all the time, so the composition of the mixtures will be fluctuating as you move along in time. You need properties like the solubilities of these elements, heat capacities, thermal conductivities, and chemical activities. And those databases simply do not exist. So what can one do? Well, one can make some progress by thermodynamic modeling, in order to find out the thermodynamic properties. So, for example, one can construct a phase diagram for the system lithium fluoride, thorium fluoride, plutonium fluoride, and study the solubility of plutonium fluoride in lithium fluoride, thorium fluoride, by having available information on all of these binary systems: lithium fluoride, thorium fluoride, lithium fluoride, plutonium fluoride, and thorium fluoride, plutonium fluoride. Unfortunately, even this system doesn't exist. There's no data known. However, it would seem that cerium is a good analog of plutonium in this system. So we have a phase diagram here which is constructed from thorium fluoride, cerium fluoride. And by combining these elements within a thermodynamic model, and I stress it is a model, one can come up with predictions about solubilities of, for example, plutonium in these mixtures of different compositions. You can see appreciable variation. You can see these solubilities are not high, so this issue of plating out of plutonium in the heat exchangers here is a real one. You can see that the temperature dependence of the conductivities are quite high. So what I've got here are the predictions of these thermodynamic models, and here are some spot experiments which have been done at ITU in order to check that the model's working. So this is certainly one area of progress in understanding this work. But what I want to talk about is my own work here, which is approaching this same problem of studying these melts by atomistic simulation. So the sorts of technologies that I've been developing over that 25 years is to develop realistic molecular dynamics simulations with particular types of ionic interaction models in which the parameters are determined by performing first principles electronic structure calculations. In other words, these models start from electrons and protons. They start from fundamental physics and build up to putting parameters into these model simulations without empirical information. So they become truly predictive simulations. A big advantage of doing this is that it's a general methodology because it's based upon basic principles. So I can gain confidence in the way this will work, say, for lithium fluoride, thorium fluoride, from the work that we've done on other fluoride and chloride systems. It's a general methodology applicable to a wide variety of ionic liquids. And of course, one of the other big advantages of this way of making predictions of material properties is you don't need a hot lab to do your experiments in. You can work on radioisotopes, and it doesn't damage your supercomputer. So this is a general applicable approach and would enable you to take out of the spanning the whole composition range, which you require here, by direct experimentation. You would need experimentation at certain points, but to interpolate between those experimental points, one could make use of this sort of information. So the output of a molecular dynamics simulation of the type I just described is a trajectory of all the ions in the fluid in a given thermodynamic state. You follow around the positions and the velocities of all the ions. The blue ions in here are thorium ions. The bronze ones are lithium ions, and the green ones are fluoride ions. And by averaging functions of these positions and velocities, you can calculate observable properties. So over here, I've got another realization of the same kind of system. One of the things that you can see is that around the thorium ions, the blues, there are a close coordination shell of greens, of fluoride ions. And the chemistry, the relative chemistry of these elements is really very much connected with those coordination shell structures. So when one comes on to talk about interpretation here, it's a great deal about what one can learn from simulations about those coordination shell structures and the way they might change from one element to another. So the general process then is one sets up a simulation as I've briefly outlined. One then seeks to validate it by comparing predictions from the simulations with experiment. One then makes predictions on quantities which are not known about, and you also provide the armory to provide, as it were, chemical interpretations of the way different materials behave in different ways from each other. So just to illustrate validation, this is quite an old slide, but here, and I've stressed how the structure of the fluid is the key to understanding the influence of the chemical properties on the physical properties. So this is comparing some predictions with these simulation models with experimental data looking at the structure of the melt. So these are X-ray diffraction experiments here. These are neutron diffraction experiments. And this is X-ray absorption fine structure. Each of these experimental probes looks at the local structure in a liquid in a different way, but you can see that this one simulation model is reproducing that data extremely well. So in this case, I can have a great deal of confidence that my simulation model is behaving in the same way as the real material. I can also calculate transport properties from the positions and the velocities of the ions. So here are some, in fact, for lithium fluoride, thorium fluoride, these are some calculations of the viscosity of the melt as a function of temperature. And here are some calculations of the electrical conductivity of the melt. The solid line here is an experimental curve from that database that I already showed you. And the red line there is a direct comparison with experiments. So you can, again, validate the properties of this simulation by direct comparison with experimental data. And then you can go on and make predictions. So this is looking, this line here represents that freezing line of the lithium fluoride, thorium fluoride mixture as a function of the composition. And these are predictions of the viscosity across the full useful range. You can see that the fluid starts to get pretty viscous when you get down close to the eutectic composition there. And so remembering how rapidly that fluid was being cycled in my reactor, you might well want to stay away from this point in the interests of maintaining good flow properties and avoiding turbulent regimes. You can also, for example, look at this figure of merit for heat transfer. Whoops. which involves a combination of all of these properties: heat capacities, densities, viscosities, thermal expansion coefficients, and thermal conductivity. Now, the thermal conductivity is an interesting property because it's really hard to measure it in a molten salt because of the high temperatures, because of convection, and so on. And so our predictions may well be more reliable in this case than any experimental values. But these then are, again, scanning out the figure of merit for heat transfer in laminar flow across this full composition range. So one can perform this interpretation and link the behavior observable properties to the underlying atomic scale structure to provide an interpretation of the behavior of different materials. So this is our favorite fluid here, FLEB, or lithium fluoride, beryllium fluoride mixture. And at this composition, it's equimolar lithium fluoride, beryllium fluoride. And again, you can look at these coordination motifs here, where in this case, because a beryllium ion is a lot smaller than a thorium one, each beryllium ion tends to be surrounded by about 4 fluoride ions in a kind of a tetrahedral arrangement. And you can decorate your tetrahedra there in this way. And now you can see that the liquid is really this kind of network of interconnected tetrahedra. They're connected because a pair of berylliums here share a common fluoride, so that their coordination tetrahedra get linked together. And if you go on to change the composition, and so this is the dilute mixture, in fact, which we've just been talking about, 3 times the lithium fluoride to beryllium fluoride, you can see it's a relatively uncoordinated, relatively isolated beryllium fluoride tetrahedra. But when you change the composition, increasing the beryllium fluoride content, you can see that this network-like structure becomes more developed. So it doesn't take much imagination to imagine that because you've got all of these tie lines flowing through your fluid, that the viscosity of this system would be much higher than this one, and that indeed is the case. This is a comparison of the viscosity of the FLEB system obtained in experiments. That's Oak Ridge data, and these are predictions from our simulation models, and you can see they agree quite closely, and that increase of the viscosity is very much connected with that interconnectedness of the coordination tetrahedra. So those are transport properties, structural properties. For simulations, thermodynamic properties, at least thermodynamic properties relating to free energies, are more difficult. You might well be interested in such things, for example, to understand the behavior of the solubilities of different elements. The reason it's more complicated for a simulation is a free energy involves the entropy of the system. And you can't get the entropy of a system simply by following its trajectory. You need to know about the global phase space that's available to it, so you can't do it directly. So here I'll just illustrate what you can do instead, which is to relate the thermodynamic properties of 2 systems to each other within a simulation. So I'll illustrate it by talking about the thermodynamic activity coefficient of, say, a trivalent metal system here, and that would be related to the separability of the fission product in some kind of pyroprocessing device. So the idea here is that you would dissolve some fuel which might contain several species that you'd be interested in, like uranium, plutonium, minor actinides in a trivalent state. And you would, by changing the electrical potential between the anode and the cathode, you would try to systematically deposit one element or another. So, and this would happen, for example, in a molten salt solvent system. So you're trying to go from some initial concentration of element M, initial concentration of element N, to a final composition of element M, where you haven't deposited any of the element N. So the separability would be, if you could achieve this, and this was a very low mole fraction in the solvent, you would have separated M from N. Now it turns out that the separability in this system depends upon standard electrochemical potentials, electrodeposition potentials of the metals, say with respect to their pure molten salts, but also on these so-called activity coefficients. So the activity coefficient measures the, as it were, the happiness of the of element N in this particular solvent conditions. And one might hope, in engineering this sort of process, to fiddle about with the solvent in such a way that you change these activity coefficients in a favorable direction. Anyway, these activity coefficients are my example of a thermodynamic property that I'd like to obtain from a computer simulation. So it turns out then that if I were able to study this, as it were, chemical reaction, where I take MCl3 dissolved in this lithium chloride, potassium chloride mixture, and I combined it with pure NCl3 in the liquid state, and I converted that into NCl3 in the solvent system and pure MCl3, and I was able to measure the free energy change for that process, or obtain it from a database, for example, then that free energy change would directly give me this ratio of activities that I'm interested in. So how am I going to get that in a computer simulation? Well, I want to carry out this chemical reaction, and I can carry it out in 2 steps. Firstly, in a simulation, I can take my mixture system and I can transmute element M into element N. Transmutation in the simulation simply means I change the interaction potential from that describes M and its interaction with its solvent to that which involves N. So here I need to carry out 2 transmutation steps of M to N in the solvent system and of N to M in the pure system. And as I've already said, the Gibbs free energy change for this process gives me my ratio of activities. But the clever thing is that I can achieve this by so-called thermodynamic integration, by stepwise changing M into N in a series of steps, lambda going from 0 to 1, I can change, for example, uranium here, which is a large ion and has a big coordination shell, into a scandium ion, which is a small ion with a small coordination shell, and I can do that in a series of steps. And by measuring the work that I'm doing to change that to that, by dragging off these coordination shells and changing them into that, I can get the free energy changes that I want. So this is the way you do it. You do it in a series of steps where you're progressively changing from uranium to scandium. You average this quantity over the simulation run. That gives you this series of lines here, and you integrate it. I'm interested in the difference between the free energies for each process. So actually my desired quantity is the area between these 2 curves. And then you can compare those activity coefficient ratios. Well, actually you can compare the electrodeposition potentials with experimental ones, and you can see that they're performing quite well. So what I've done there is I've done this thermodynamic integration to compare 2 systems. To do an absolute measurement of the activity coefficient would be extremely difficult. And then in the context of interpretation, you can see that these ratios of activity coefficients in fact scale quite nicely with just the size of the cation that's involved. So one can provide an interpretation, for example, of why the electrodeposition, the solvent effects on the electrodeposition of scandium with respect to, say, uranium or lanthanum would be why they are. And you can go further into the simulation and examine that even further. So, in conclusion then, this modeling methodology is generally applicable. You don't need a hot lab to do it. It's capable of predicting material properties and also helping to interpret material behavior. And the accuracy of these simulations, accuracy at the level of accuracy that's required for application in engineering models, has been validated on the molten salts of interest. So thank you for your attention.
Yeah, thank you indeed for this very timely stopping, which helps us with this long day. Please go ahead.
I'm Ganesh from BRC, India. Presented a very nice modeling approach. It's very important because we can't do experiments at high temperatures. But my question to you is, before taking this complex systems, have you validated your method? For example, in the case of liquid lithium, I talk of measured specific heat, ultrasonic velocity, and density as a function of temperature. It is available up to some point, but one would like to have them up to critical temperature. So have you done for simple liquid metal systems your methods and validated before proceeding to these mixers?
So I've done lots of work on simple systems, but they would all be molten salts, because the type of modeling technology that I'm using here implicitly assumes that my liquid is made up of ions, which are not exchanging electrons with each other in a major way. If I were to describe lithium, lithium is a nearly free electron metal. The electrons are flowing around. I would need a different modeling technology. As it happens, I have also worked on that, or similar things some time ago. So the answer to your first question is, have you worked on simple systems? Answer, yes, but they would be molten salts, and I would need to get simulations on the timescales long enough to do, for example, those thermodynamic properties. I would need to develop another technology. Well, in fact, there are other technologies which would work, but they're not the same ones as the ones that I've just been describing here.
Thank you.
Okay. Yeah.
I'm going to go in the other direction. Have you considered, or you plan on going in the direction of adding essentially fission product surrogates or interactions with materials for the pressure boundary?
Absolutely. So by fission products, you mean, say, minor actinides and so on?
All fission products.
Oh, yeah, well, so any ionic fission product, indeed, yes. And we've done work on the rare earths in here, and what I would have difficulty doing is doing, say, gaseous product, the rare gases, for example. Again, I'd need a different interaction models. Well, it might work. I might be able to do that, but I'd need a different type of interaction model in order to deal with things like xenon in these molten salt mixtures. But it's an interesting possibility.
Okay,
that one might work, whereas applying these methods to lithium metal would not work.
Okay, last question.
I'm sure there's a good reason, but I can't think of it. Why does your circulation time have to be so amazingly short?
It's because it's that 1.5 gigawatt requirement, which is a sort of generation 4 type target. And I think if you start thinking about how you're going to get the requisite amount of fission going on and then get the heat out, that's what drives that time. As I said, Elsa Merle-Lucotte will be here. Well, she'll be talking on Wednesday, I think. She's done, or she's been the driving force of the thermal hydraulic modeling, and also that coupled with the neutronic analysis. But that's what it comes down to. If you take that system and you say, I want 1.5 gigawatts electric out, that's what you have to do.
Okay, let's stop here, and you will ask this question to Elsa on Wednesday. Okay, last speaker of this session, please.